Hi, this is Rebecca from BrainBox AI. In today's podcast, we're going to be talking about neural networks and their application in the field of engineering in order to make it more relevant and efficient to real-world cases. More specifically, we're going to be talking about this concept called neural ODE, which stands for neural ordinary differential equations, and specifically how we are applying it to BrainBox AI's operations. What's really exciting is that it's a novel concept that has never been done before, where we are applying neural ODE to AI predictions in order to make them faster and more sustainable. So it's really a world first in terms of AI contributing to saving the planet. To talk about this, I'm joined by Professor Pierre-Luc from Mila, which is Quebec's Machine Learning Institute, as well as Jean-Simon and Mathieu from BrainBox AI's Artificial Intelligence team. Good morning, everyone, and thank you for being here on this new episode of the BrainBox AI Podcast. And today we are joined by many special guests from BrainBox AI and from Mila. And we're going to talk about neural networks today, something I'm a very big professional in. If you can't sense that, that's sarcasm. So we're going to start with a little round table of introductions. Jean-Simon, would you like to get us started?
Yes, absolutely. Jean-Simon Venne, CTO, one of the founder of BrainBox AI. Pleasure to be here this morning.
Thank you for being here. Pierre-Luc.
So Pierre-Luc, I'm a professor here at University of Montreal in Mila. I've been collaborating with BrainBox for more than a year now, so we're going to be discussing some of these interesting research projects we had together.
I'm Mathieu Le Cam. I'm a researcher at BrainBox AI for a bit more than a year now.
Nice to have you here. Thank you all for being here. So let's start with setting a bit of groundwork. Jean-Simon, could you just tell us a bit of who BrainBox AI is, what we do, what our mission is? Just give our listeners a bit of a base.
Yeah, absolutely. So what we do at a very high level is we try to use different AI tools to optimize the energy being spent by building, more precisely commercial buildings. So if I dive a little bit into the detail, the opportunity really came upon us regarding the fact that these commercial buildings have already control system. And these control systems generated a large quantity of data, which is most of the time not really used more than real-time controlling. So we basically connect to these control systems, we extract all of that data, and we use that data to train deep learning models. And what we're really after is a prediction. And that prediction is then, if it's the good quality and accurate, is then used by different algorithms to look at what are the different control options or scenario we should use using that prediction. And then these algorithms will modulate the building in real time. So for us, the quality of the prediction is extremely important. So how do we basically build that prediction? How much data do we need? And the quality of that prediction is pretty much the most fundamental part of BrainBox AI.
And what's the ultimate mission of BrainBox with those predictions?
Well, the ultimate mission is when you really look at all of the building space, it's about 1/3 of the energy being consumed on our planet. Mm-hmm. And we could quite easily compress that by a good 20 to 25% reduction of the energy. So really putting all of that building stack up to work to really help to reduce the global warming effect on the planet.
Saving the planet, it's such an ambitious goal.
Absolutely.
Awesome. So I guess today the topic at hand is neural networks. So we have a description of BrainBox AI now. Pierre-Luc, if you could give us just a definition of what neural networks are. More specifically, and I'm going to read this one, neural ordinary differential equations. If you can explain that simply, if possible, that would be great.
So do you want a lecture or just...
Simply.
Let's start with neural networks. Here's my definition, the way I like to think of neural networks, and I think it's going to set the stage for actually neural ODEs afterwards. To me, the paradigm that we're experiencing right now, which by the way is more akin to deep learning than neural networks. So neural networks is basically belongs to that general family of methods, deep learning. But the paradigm we have here is we're able to essentially write programs, but then learn those programs thematically. There's another term which I really like. It's called differential programming, and I prefer to think of what we do in those terms. So why neural network? Neural network actually is a term that came from the 80s, 70s, in fact even before that. where it was inspired by research in psychology, and people were trying to mimic basically what's going on in the brain through mathematical models. So this is how things evolved in the 80s. It was called connectionist method, so on and so forth. Then it evolved to different phases, and the last phase we've seen is the paradigm of deep learning, where we started being able to learn these much more complicated and longer programs essentially. And nowadays, what constitutes a neural network is actually way different than what we used to call neural network in the 80s, where it was more of a toy representation of what we think the brain might be doing. Now, it's literally differentiable programs. That's the new paradigm. So that's my definition. And the neural ODEs, maybe you can go back again, but that has to do with physics and how we can incorporate a class of methods called ordinary differential equations in physics and mathematics, and incorporate those into our programs, our differentiable programs, into our neural networks as layers, and learn those things seamlessly.
And though they've existed for quite a while, have you seen, like, recently there's more of resurgence, or is that just an impression that I have?
For neural ODEs in particular, yes. I mean, deep learning, as you know, is fueling all the revolutions we're seeing nowadays, including, generative AI and large language models and so on. But going back to neural ODEs, the popularity actually is due largely to a 2018 paper by our colleagues at Vector Institute. Was David Duvenot's group who introduced the idea of neural ODEs. That being said, if we want to be historically accurate, our colleagues in other fields had been doing similar things for quite a while, like in climate science, like all other disciplines where there's some sort of differential equation modeling. They started knew about those techniques. Now, this is acknowledged by Duvenot's team, and then in the paper, it's, they say, well, we use that method called the joint method. It was known, but we should largely credit them for popularizing it and also making use of that trick way beyond what had been done previously. So yeah, that's fairly recent, 2018, and then there's been a lot of work extending those ideas to even more complicated models, physics model, partial differential equations, and so on, and keeps them going.
Significant progress in the last 5 years. Interesting. So now we have the definition of what BrainBox is, the definition of neural networks. Mathieu, you are our day-to-day AI researcher at BrainBox. What brought the challenge of BrainBox AI to neural networks?
Yeah, so, well, as Jean-Simon mentioned before, so we have this goal at BrainBox AI where we want to optimize the heating, ventilation, and air conditioning systems in buildings to reduce the energy use while preserving thermal comfort. And one way to do this is by using a predictive control strategy. So in this type of approach, you have an optimizer that will try and reduce this multi-objective goal where you have the energy use, but also you want to minimize the discomfort also. And one way is to use this optimizer together with a predictor that can tell you what's the best control strategy, when you need to activate your systems, for how long, so that you have the least amount of energy used, and so you need to have this predictor to tell you what's going to be the cost of different controls approaches. And as Jean-Simon mentioned, we want to be able to deploy our methods, our algorithms as soon as possible in the building. So you want to have a solution that is easy and fast to deploy. And what we've seen so far with deep learning methods, like Pierre-Luc mentioned, is that they need quite a lot of data to be accumulated so you can train your model and be able to have a forecast that is accurate enough to be used in a predictive control strategy. And one thing that we were very happy with when started and testing neural ODEs approach is that we don't need as much data to train the model and reach similar forecasting accuracy. So this was a big a challenge for us that we were able to tackle with the neural ODE approach. So that's one of the things that of course it's also very useful for the fact that we do have knowledge about how the thermal dynamics in the buildings, how the temperature is changing, what is causing this, so we can put all this prior knowledge inside our models. The neural ODE lets us put all this information that we have, and we end up with a model that has less number of weights of parameters to learn compared to a deep learning approach. So it doesn't need as much computational power to train the model. So that's also good for us. It can be trained on a CPU compared to GPU for deep learning approaches. So we can also reduce our energy footprint when training all those models that we want to deploy in all the buildings, all the that we are covering with BrainBox AI. So it does present quite a few advantages. It also has, what's also useful is that it has a physical interpretation. So as I said, we put in our prior knowledge and we can learn from those physically interpretable models. We can extract information that can be useful in other contexts, like we can extract the thermal mass, thermal inertia of the building that can be used for demand response events when you want to know, okay, if I'm turning off all the systems, how long is it going to take before the temperature drifts and reaches uncomfortable conditions. I mean, we can get a lot from this, and that's why we were very happy to see what we could get with the neural ODEs approaches.
And how did the relationship start? I mean, what's the story behind that?
I think we've got we're lucky to be in the position here in Montreal where there's great interaction between industrial sector and the economic sector. So I think we've met through actually our great team here at Mila, who's been putting us into contact, and then it's just a matter basically of connecting at the research level. And of course, there are very interesting challenges here, and so that's how it started essentially. I was also interested myself in using more neural ODE approaches. So in fact, my main research here is a reinforcement learning researcher. So I'm interested in the problem of learning to take good actions to optimize some notion of reward, right? And there are different flavors of reinforcement learning, but let's say one of the dominant paradigm in reinforcement learning are the techniques we've seen behind, let's say, the results in playing Atari games and so on. That's one kind of RL. But I like to think of reinforcement learning more broadly as the problem of learning from data. And in that sense, RL is not so much a particular technique than more a problem. Mm-hmm. And in that sense, what we're doing is reinforcement learning. It just happens so to be using neural ODEs, but we're learning from data. We're learning to take good actions from data. So this is reinforcement learning to me. So I think, we've met at a point where in my career, I had started taking this shift where I wanted to broaden the set of methods that I wanted to explore in reinforcement learning. I've worked a lot in video games, in Atari, things like this. Not because I like to play video games, but it just happens so that our benchmarks are often built around these things. And here's the thing that I realized. It's one thing to chase a number and a benchmark, but ultimately we have to ask ourselves whether the algorithm we developed in the end has any use down the line in real life. And that's the some of the main criticism I had when I started shifting a little bit my research interest. I wanted to verify whether what I was doing had any value in the real world. And it kind of led me towards, well, first off, looking at their methods and also looking at more meaningful problems so that we get a signal from the real world. Are we going the right direction? Because the space of possible things that one could research is so broad that it's easy to get lost in work on, well, ultimately, I mean, you've got to like what you do, so I don't want to say like useless things. If you like what you do, well, it can be useful in a way, but we need some signal, we need some grounding in the real world at some point. So that's how it happens.
There's probably nothing more meaningful than working on a solution that helps fight climate change.
There you go. There you go.
Absolutely. I mean, the entire story of BrainBox is all about core research, right? So we did it with Université de Montréal at the beginning in Polytechnique, then we went to TS, McGill, Concordia. Ivado was all core part of the mix, and of course Mila. And the reason I think we're progressing quite rapidly right now is because of the partnership we have with Mila, which is pushing the envelope always further down the road of how can we use these tools, which are, to your point, used in sometime in other industry, and how can you like use that kind of how they used it in like the video game in this way or in the telecom sector. I remember when we did the co-research with TS, we were taking basically the leading professor was somebody who was expert in telecom, how do you optimize the telecom network, and it was like we're taking this technique to say how can you optimize the energy flow in a building, which was kind of it's kind of the same when we think about it. So it's different data, different equation, but it's like there is a parallel where you could piggyback on it and learn from. So it's been the entire story of
cross-pollination, opportunities.
But I'd say too also this particular problem space in which you are is a great fit for reinforcement learning. No, I wouldn't say that of all problems. Although I'm a reinforcement learning researcher, I would like to say that you should do RL all the time. The reality, unfortunately, is that not all problems lend themselves well to a reinforcement learning method. But here in this particular problem, we have one key element, which is oftentimes access to great simulation, which on its own simulation is not enough, but it's a very important starting point. There are problems where it's not the case. But from now the experience I've gathered in this collaboration, I can see that this is a key element, like having access to good simulation, as opposed to having access to troves of offline data, the way that we would typically require in supervised learning, in traditional machine learning techniques. So the presence of good simulators is actually very important, but not enough. At some point, we also need to incorporate data, which is why we do that modeling, which is why we do those neural ODEs, and which is why we incorporate prior knowledge, but we then supplement that prior knowledge with learning flexible models that basically account for the stuff that we cannot model perfectly. So.
I was gonna add on the topic of using simulators for reinforcement learning. I mean, you do need to. If you have simulators that are good enough so that you can learn valuable information from those that you can then apply in the real world. I mean, we've seen some great examples with robotics where they were able to learn a lot from simulation and then be able to apply it. But what I've seen, and I find it's more challenging in buildings, is that the gap between simulations and what's happening in the real world is sometimes very big, and it's hard to make use of whatever you've learned in your simulator. So you will need to find ways of putting more uncertainties or I don't know how. Do you see how we could apply this into buildings and buildings thermal dynamics? For going from simulation to reality, I find it's not always that easy.
Yeah, well, but it's a good point you make here. In robotics, indeed, this is a very. In fact, you're kind of robotics researchers. Because you happen to have a very big robot in which you actually live. But that's basically a robot. However, as opposed to many robots we see nowadays, you don't really do vision-based robotics, right? So one of the main advances that has been seen in robotics to account for this sim-to-real transfer problem has been techniques like randomization. Essentially, you introduce noise in your image at train time to make your system more robust at inference or deployment time. The analogies are not one-to-one here with buildings, but we can draw inspiration from those things, and I think this is going to be subject for future collaborations, I think, and that'll be a very rich topic as well. So we can draw inspiration, but also there's unique challenges that you're facing in this problem space.
Yeah. It's really a world of multi-robot, multi-objective.
That's right.
And how do you optimize the entire equation ecosystem?
That's right. And I think that's another interesting axis of the problem is the multi-zone aspect as well, or maybe even multi-building, I don't know, but there's this, you could view it as a decentralized problem, you could view it as a multi-gen problem. All these different modeling choices, they all come with certain trade-offs, but it's a very rich problem.
We're not done yet.
There's ways to go. I just want to go back on Mathieu's comment with regards to the results of the research and its impact. We gained a lot of speed. Can you speak more precisely to the amount of speed that we achieved?
Yes, so on the advantages that we've got from this type of forecasting approach with null ODEs, so quite a few advantages. So in terms of amount of data required, as I said, we significantly reduced the amount by like 10 times. We used to have to wait for weeks of data being available to train our model, whereas now with just a few days of data we are able to reach the same accuracy. In terms of speed, so I mentioned that compared to deep learning approaches, where you'd have hundreds or thousands of parameters that you'd have to tune and learn from the data, here we only have a few, because we put a lot of prior knowledge in the way we shape the equations and the model. We only have to learn a few parameters that have a physical interpretation, and that makes it so that we can train it on CPU, so it's less, it requires less resources to train. So, yeah.
If I may just make a little precision,
Yes.
I just want to highlight though that here it's not like neural ODEs against deep learning. Really, it's about, because we're still doing deep learning, but it's the question here is, if you got prior knowledge, if you got knowledge about the physics, thermodynamics, so on, let's make use of that and still do some learning. There's still deep learning models involved.
Yes.
But really, the trade-off here is: do you go completely black box, or are you physics informed? Yeah. And this is where we're working together. We're physics informed. We know that there's structure in our problem, so we don't go fully black box. It's more of a gray box approach, essentially.
Yeah, Pierre-Luc is completely right. I mean, there are still some terms that are difficult to estimate, and for which that we need to have some kind of black box approach, which is also plugged inside this differential equation. So we take advantage from both worlds or both approaches. So yes, thank you.
So it's fascinating, right? So it's you require less data. You're still doing deep learning, neural network, fine, using less data. So you don't have to wait to collect an amount of data X to do the start modulating. You're doing it less computing power and spending less energy on these computing power. So it's really like optimizing on 3 different axes. Which
It's
is
faster, it's more environmental, it's more efficient.
so.
Yeah, and I think also we've alluded to this point earlier, but interpretability, in my experience as well, when it comes to real-world applications and industrial products and so on, is very important.
Yeah.
Oftentimes, the clients or stakeholders, they want they need to gain trust, and that's completely understandable. They need to trust their system, And trust and explainability can be offered in different ways. And it can, multiple layers of explainability can also be stacked on top of each other. But going back to neural ODEs, at least domain experts can look at them and say, well, that makes sense. And then once we learn a system end to end, we can then inspect it perhaps more easily than if we had chosen to go fully black box. So that's very important for real world applications. Because we need to be able to verify our system. These, especially, you're deploying those systems in buildings. I don't want to think about what could happen if your controller, goes crazy. So you need to be able to verify, give insurance to customers that the product is going to do the right thing.
And also basically improve the safety.
There you go.
One into it.
More robust.
Yeah.
Interesting. And maybe just a last little point on the project. How many researchers were involved in it, and how long did this take for us to make happen?
We've been working together. I don't know, with COVID and everything, kind of last track of time, but we've been working maybe together for a year and a half, perhaps.
Something like that, yeah. I'm also confused with the COVID. But yeah, I think it's about 18 months.
A year and a half. We've had various students in my group. We have Vincent, who's been playing an active role, who's a PhD student, and he's also an expert in HVAC systems, but has been deploying those neural ODEs, has been driving the project. Various students, some of them have graduated, but have been involved in that project. We have Nikki, who inspired the initial collaboration. So Nikki put in place this toolbox and also demonstration of an idea in which we use neural ODEs as layers in the neural network, but essentially differentiable optimal control layers. And he published that toolbox called Mila, who was basically the starting point for collaborations. We started experimenting with that in the very early days. And so Nick is still a student in my group, PhD students.
I've joined the project a bit later, so I've only known Vincent, but I was very happy with all the great work that he's done, and also he's been winning this prize about the vulgarization,
scientification.
And I found that he had been doing a lot of work and exploring different shades of neural ODEs, from continuous to discrete state space models, with encoding or not into a latent space, the partially observable environment. I mean, he's been doing a lot of great work. It's a good
collaboration.
Yeah. Just an anecdote here, but Vincent is so he got started on a project, and I said, here's what we want to do. He knew about neural ODEs, but he hadn't actively worked on those things. And Vincent basically came 2 weeks later and was like, all right, I've done it. It was just like an amazing productivity. Not to say that we're done with the project in 2 weeks, but he's been working at such a impressive pace. We've been able to go much beyond the obvious since he started working on those topics. So
perhaps we should invite Vincent to our next podcast. That might be a good good sign. Jean-Simon, you're the CTO of BrainBox AI. This amazing research. How are we protecting it? Is there any sort of patenting work that's happening?
Absolutely. So we're patent pending right now. So we're following the process to obtain the full patent. I would say that we're also in parallel to that, moving toward putting neural ODE in production. So we have this, I would not say legacy, but we have this existing neural network MLOps in place, which is basically training the model and retraining the model when the prediction accuracy tend to depreciate. So it's an automatic system which is running every night. So we're going to basically start to introduce neural ODE to that MLOps system. So it could be put in production, and all the building could start to benefit from it. So that's happening in the next.
That's an interesting part, right? Operationalizing the
Yeah.
technology. That's as hard as probably developing the models.
And monitoring, and that's a very tricky part as well.
That's mainly what Mathieu is doing now. He's educating the ML ops team, because they're looking at it going, we're fine right now. Why should we? So Mathieu is making a lot of explaining how it's going to work and why they should basically put it in production.
Lots of communication challenges ahead of you. Or?
Yeah, I guess it's a good teaching opportunity for me too, and making sure, when you're in research and you are working in your little bubble, and you always dream that whatever your baby that you are giving birth to is gonna be used in the real world. So it's a nice accomplishment, I think, to see that this is gonna go to production.
Actually, that actually reminds me, another challenge, another thing to take into account is if you want to be more efficient with the data you use and so on, that aspect of retraining, because the data distribution drifts, that's how we call it. We have so when your data distribution drifts, your problem changes a little bit, and not all methods actually do well in that regime. In fact, that's one of the main challenge with black box deep learning methods. This has to do with what we call out of distribution generalization, and that we don't do really well. So this is why it's important to have, let's say, hybrid models like we have, because they become more nimble. They can adapt more quickly. It's not like you're trying to change these gazillion parameters all at once, which is very difficult to do. You can adapt more quickly, and that's very important.
And people don't realize, right? People will do first experiment, but they don't think if you go in production, you're going to need to have all of these retraining feature in place and safety. And it's really these kind of barrier to really put something in production. So
the degree of adaptability.
Yeah.
Awesome. And I guess, where is this all heading? It's so exciting. Is there a next step? Is there a new project?
So there can be a lot of them.
Yes, there's so many avenues.
So I think Vincent's working actually on probably writing a paper about some of the findings we've had. We're working in an open research environment, so some of these ideas will be communicated. So this is happening. I think there are very interesting problems that we could pursue around the question of stability, robustness, that I think are very important, and it also intersects well with some of the concerns that as a whole our community has on safety or system in general. This is one particular kind of safety that is very concrete, very real, for which there's a real need. So this is where we might be heading, I think.
Yeah, so the entire world of safety, and we call it the health. So what is the health in the operation right now? Are you doing the right decision? How do you know you're doing the right decision? So what are your different safety in place that are vetting that you are doing autonomous control the right way? Interesting field.
Super important.
I was gonna say on the control part with the reinforcement learning, we've touched a bit about the simulation to reality. That would be something really interesting to look into, but also when I'm thinking about using reinforcement learning in the real world, having some kind of safety, as you mentioned, in place, so that it wouldn't take any action that, because I'm not an expert in that field, and maybe you'll correct me, but if it's learning from trying and testing different control strategies and then learning from this to then try and find a better strategy to control the HVAC systems, then we don't want it to go and
yeah, the problem exploration. So the techniques we've been developing so far are not online in the typical sense that there's active exploration where the system is going to crank up the temperature in your building just to see what happens. Yeah. That's not going to happen. But indeed, at some point, it's very useful to go and do active data collection, which is a problem of exploration. That's largely an open abstract problem in reinforcement learning, and we could certainly take some inspiration from what happens in the real world beyond our classical exploration problem in Atari, which has been to have the little agent in Montezuma's Revenge go get the key to open the door. It's difficult exploration problem, but there's just so much you can do about this at some point.
Exactly.
Right?
There's limitation.
Yeah.
Fabulous. So we are at the end of the podcast questions. We usually finish off. Well, does anybody have any last thoughts? Anything that we didn't cover? That
I just maybe to share for fun. I've been renovating a house in the meantime while we started this collaboration. And I found a new passion in the world of HVAC.
That is a rare passion.
And I sort of went a bit overboard and nerded out big time on our HVAC system at home. It doesn't have BrainBox, unfortunately, because it doesn't have a backnet interface or anything. But I just wish I had gotten it though. But yeah, I've been building a new system, hydraulic and so on, and I have my little HVAC system in my house, and it makes me think about our collaboration every time. Last January, it got really cold in January, and I had to learn lessons from our collaboration. There are various strategies sometimes that are implemented as heuristics, but none of our agents actually find them. But one of them that had been told is that, well, if your system struggles actually to heat up your house by minus 35 Celsius, maybe you can preheat your house, let's say 8 hours in advance. So I did the preheating strategy, and actually I went through the minus 35 thanks to that wisdom that I've acquired in that collaboration. So there are benefits as well beyond the
Jean Smal's HVAC passion is contagious, it seems.
It is.
Is your family happy to be living in a living lab? Or
That's so good. It's very comfy. I make sure that everybody's comfy in the house. But I'm playing basically the role of the brain box. I'm a human brain box, I guess.
More manual, but yeah.
There you go.
Okay, so to close off the podcast, when we have a special guest, we usually end it off with fast questions. So, Pierre-Luc, if you're game to give us a try, 2 phrases or less for each of these answers, and this will conclude the podcast. So, here we go. What's your favorite LLM at the moment?
I use ChatGPT-4 a lot for my teaching, for all sorts of things.
Okay.
Yep.
In which industry sector do you believe neural ODE can have the biggest impact?
HVAC is an obvious one.
Yes.
Process control would be another one.
I was hoping you'd answer HVAC. That's great. Who is your favorite AI thinker or researcher right now?
Good question. That one's a good one.
There's a lot of them, eh?
Yeah, I'll say my former advisor. I have a really good relationship with her. He's doing Africa.
Oh.
So I'm going to say that. But I don't get to work enough with her, unfortunately.
Maybe she'll hear this and she'll reach out.
Hopefully.
And then lastly, what is the best book you've ever read? And I'd like to add, it doesn't have to be about AI.
That's, I've been reading recently, and it's been influencing my thinking about science a little bit on the philosophy of science, and essentially how we can, there are different ways to think about science, but one of them is through the lens of anarchism. But that should be for another podcast. The point is, that book influenced me a lot because I think it's important to adopt a pluralistic perspective on science. That's actually in the name of my group, plural, as in pluralistic. That's because of the book, but we should have another podcast to talk about it.
Fascinating answer. Yeah. Okay. Well, thank you all so much for joining us, and maybe there'll be a part 2. Look forward to it. Thank you.
Thank you.